Okay, so presumably the recording is going on right now.
Perhaps. Yes, it is.
Okay, now I don't know what this is, requesting remote control of your shared content. Is it, what is exactly you want to, I mean, if we're good to go, I'm not sure there's anything.
Yeah, it's cool, it's cool. I sent that.
Okay, so I'm going to go ahead and decline that as long as everybody can see it and I can hear your questions. So let's do okay, so I mentioned the chapter 4, that would be the last chapter 4, homework 4. That'd be the last homework on the, I believe it was in chapter 2, and we're currently in chapter 6, and I ginned up a few of the, since we had started the topic, I ginned up a few pages to do a short review, which should take us pretty much where we were when we left off. And so it's a little faster than the original, but that may not be a bad thing. Okay, so stop me if you got a question. I'll just remind you that the chapter 6 topic was Fourier series, and the Fourier series is useful. Hi. It's not critical, but I was kind of wondering why it is I'm not able to get that. I mean, like before, I did everything I could to get it on get the whole screen on there, but believe it or not, I was having trouble.
Right now, you are sharing the document camera?
Yeah, but actually we're okay. They say they can see it fine. So I'm apologize. I brought you here. It wasn't an emergency. Now that I thought it was an emergency when I pushed it for the request, but I realize now that they can actually see a bigger percentage of that page than I can.
Yeah, the only concern I have is maybe the recording is just recording your desktop and not the actual page.
The recording will have both the document camera and the shared screen.
Okay.
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 So the document camera it'll be included in the recording.
Okay. Okay. This is not critical now, as I see it. But if something quick you can fix so I can see a bigger picture of the screen and what I have here. I mean, right now before I had like almost the whole thing there.
Right now I'm gonna right-click your video.
Oh, Spotlight. That's right. Spotlight does something.
And that
prevents them from.
Spotlight makes this video the primary video.
Okay.
For, all of the participants.
Okay.
And, right now, because you have you're sharing your screen as well. In order to get a bigger view of this, we'll need to go into your video settings. And under share screen, we're going to enable side-by-side mode.
Oh, okay. Okay, I remember that. Side-by-side mode, all right.
I'm going to end the share.
Oh yeah, well that looks great, okay. All right. So we even got the chat down there at the bottom now. All right, that's great, okay. Oh, but what happened? I mean, in between you had exactly what I was looking for, but now it seems to have gone back to what, oh, that looks good. That's kind of what I wanted.
Right now,
but
this is just the document camera. Are you needing to share the desktop screen as well?
No.
Okay.
I just want them to see the document camera.
Great. Before you were sharing the computer screen as well.
See, I couldn't get out of that mode, but now that I see.
To stop a share?
Yeah.
Up at the top, if you click the red
Stop share. All right. So that when it says share, it's desktop share.
Yes, sir.
Okay, that clarifies what sharing I'm discontinuing. Okay, got it.
Sorry about that.
No, that's great. Thanks. Thank you. Okay, so I'm back. So let's. So the topic that we're working on was Fourier series, and all these signals that we're interested in have this property being periodic, and that goes with the language. A periodic signal is something called the fundamental, which would be 1 over the period. When written that way, that unit is a hertz. And if you take and multiply by 2 pi, it's sometimes also called the fundamental, but then that unit would be radians per second. Stop me if you've got a question on that. Now, consistent with representation of a signal with the Fourier series, we have something called the harmonics. And the harmonics are the multiples of the fundamental, and you could have those in either hertz or radians per second. Okay. Just grabbing my coffee, that's all. Okay. Now, the book covers, I mean, I think for good reason, there are 3 forms of Fourier series, which I believe are referred to, and as you do your reading, you'll see it again. Basic, in the terms of the basic form, something called the compact form, and eventually we graduate to the exponential form. And in a certain sense, there's a hierarchy here where, you know, it makes more sense to start with the basic and go through the compact to get to the exponential. Okay, and as you can see, these are somewhat different forms. You could argue they're identifiable coefficients. You know, the A's and the B's, they seem to go with the basic, and then you get these C's that go with the compact. And then you have the exponential uses the D symbols for the coefficients, D sub n. And almost what you can see, in fact, not almost every time, anytime you see a T in any of these expressions, it's always preceded by n omega naught. Okay, so if you look at all these cases, it's always n omega naught. All right. Any questions so far? Now, we introduced a way to view how to explain the formulas that are associated with calculating those coefficients. Notwithstanding the fact, you know, I cannot say that there's no value to just having seen the formulas without the explanation, but I take the perspective that in engineering, it's good to have some idea where the formulas come from. So we're going to kind of back up on that and see where these formulas come from. Now, my own viewpoint, these formulas that we're going to see are kind of based on some mathematical ideas that come out of, and I don't want to scare you off, some part of it, if you ever, any of you had linear algebra, part of it's sort of buried in there, but we don't really need that. I think as long as we have some confidence in what the traditional dot product means. So the analogy that is taken here to help streamline the understanding is that the mathematics that we're going to be using specifically to generate formulas is based on something the mathematicians could, and I guess we could call it also the same rule, something called an inner product. Now, the analogy is back to something hopefully more familiar with, well, typically more familiar with, would be the dot product, which we know would correspond to actually physical 2- and 3-dimensional vectors. And to that extent, you know, just like, you know, here we use the reason we have this analogy, the dot seems to represent these operations in both cases, the dot, elevated dot. So we can, as you know, in the traditional dot product, you can have 2 vectors that are orthogonal, meaning simply perpendicular, and you can visualize that in 2- or 3-dimensional space without too much difficulty. But when you get to this inner product, the concept of orthogonality still could be used, and the way that it is used is if you have this this rule that we have here, and if you invoke it and with these 2 functions, and it turns out that the under the definition of the inner product and the inputs being these 2 different functions, the result is 0, we call that orthogonal, almost in the same vein as you would with the dot product. And so the inner product rule There is a section in your book that covers this. The inner product rule that we are using is is this one. Okay, and where the star represents complex conjugate, and the only comment I have, well, yes, it's integration, and the time interval is the period T naught. The only comment I have on this is, besides the obvious, is that if the two functions are real, then we know that taking the complex conjugate doesn't really change anything. And we also know that taking a product is a commutative process. F times G is G times F. Therefore, if in fact the two functions are real, you could argue from this definition that the inner product of the two functions follows a commutative rule also. In other words, F inner product G within, it follows G inner product F under the condition that both of them are real. Now you say, well, you know, if we look at our three cases for our Fourier series, I'll tell you in advance that 2 out of the 3, which you might be able to already guess, we're going to be able to claim that that inner product will involve functions that are strictly real. And you can see that from the top 2. Or maybe you can guess it's going to turn out that way from the top 2. However, when you look at the exponential Fourier series, it'll turn out, because of the very nature of the way it's set up, involves the complex exponential. Then when we do the inner product involving this representation, we will not be able to make the claim that the inner product is commutative. Now, a lot of words in there, but if there are any questions, right time to speak up.
I still don't understand the complete difference between a dot and an inner product.
Well, the dot here now represents the inner product. In other words, it's a symbol that carries with it a certain definition. And the definition is right here. So in other words, it's an operation between two functions.
Okay, so instead of us using a v vector 1 dot product vector 2 equal to modulus vector 1 modulus vector 2 and cosine of the angle between them, we have them, the inner product is basically defined as the integral.
Correct.
Okay, thank you.
Okay. Now, a good example on the dot product side of the story would be, well, we know that two unit vectors associated with coordinates x and y would in fact be orthogonal. You know, if you go back, this represents unit vectors in the x direction, unit vector in the y. We know if we take the dot product between them, that would be orthogonal. And there's nothing new on that on the left side. Now, on the right side, the claim is that we can view what's happening in terms of setting up the Fourier series in a similar way. Now, let me make a comment here, and I think there's more detail in the notes, so I'll let you go back and check it if you want to. But we know that we can think of the AX and the unit vector X, unit vector Y, as sort of some sense as basis vectors. So any vector V can be represented just in 2 dimensions, let's say as a Vx A sub X plus a Vy A sub Y. And so in the language of mathematics that goes with representation, you would say sometimes the AX and the AY serves as a basis for representation of the quantity. In this case, it's just a 2 or 3 dimensional vector. Pausing here to give you a chance to ask a question. Now, the idea is, well, the claim is that on the inner product side of the story, at least as far as the first Fourier series scheme goes, okay? As far as the first Fourier series scheme goes, the claim is that you can think of a set of basis vectors, and in a sense they're basis functions because the inner product involves functions, but you can think of them as functions forming a vector space. But nonetheless, you can think of the basis under the conditions we're talking about as being set up by essentially the functions 1, pretty much the constant, but we'll take the constant to be 1, and then a cosine tied to a certain harmonic, and the sine tied to a certain harmonic. And so here we're going to, in fact, even though I only show 3, I need to be clear on this. Actually, that would correspond to n equal to 1, 2, 3, blah, 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 to infinity. So in fact, there's an infinite number of them. I'm only showing you, you know, a representation for the, let's say with n in there, but in fact, I'm thinking n could be 1, could be 2, could be 3, blah, 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 okay? Any positive integer can go in there. Okay, so really it's not just 3. There really are an infinite number of them. And so we're saying that with that infinite number of functions, basis functions, you can represent any function that you want. And that's the basis for Fourier series. Now I'm summarizing, according to my notes, some of the facts that we were able to show. And I'll remind you that if you look at, and I'm going to kind of summarize this, imagine you go back just for a moment to the inner product rule, okay, which we have here. And if we put in, let's say for our first function, just 1, which is the constant 1, and we do the inner product with the cosine taken from up here, the claim is that that's going to be 0, because really what we're doing is if n were equal to 1, you would simply have, one cycle being covered in that integration. But if n is equal to 5, you expect to get 5 cycles, but at least they're complete cycles. And so therefore you would say, well, and I'll draw a sketch here, maybe associated with, let's say, make it simple, n equal to 2. And I trust that from the picture, you can kind of visualize that if you did integrate that function, you would get 0. Because that's really what would happen. 1 times that function integrated over t naught will give you 0. The right time to speak up if that's not clear. And certainly if it's true for a cosine, you could probably argue it's going to be true for a sine. You can draw your own picture, but I didn't put a reference in there. Actually, you could argue that could be construed as a sine as well as a cosine picture. So it's going to be true for the sine. Okay, and this we're still covering, I think, material that we had touched on before we quit. I mean, at the last regular class. Okay. Any questions? Okay. Now, in addition to that, if we do the dot product between the cosine and the sine, here I have an n omega naught t, and here I have an m omega naught t. That's also going to be 0. Now, there's going to be some trig identity involving the product of a sine times a cosine, and where you can write it as a sum and difference frequency. And the argument's going to come down to the same thing. You're going to have an integer number of cycles being contained in the time interval t naught, just like we did here for both the sum and the difference frequency. And again, the trig is going to lead us to the conclusion that as long as the n and the m are different, they could be even the same. They don't have to be different since it's a cosine with a sine. But as long as it's a cosine and a sine, and the n and m can be the same or different, the result is you're going to get 0. Okay, now it gets the conditions become a little bit more constrained if in fact you do a cosine with a cosine. Now, if you do a cosine with a cosine, in order to guarantee 0, you have to say the n is not equal to the m. And we'll clarify that later. But I guarantee you, and you can look it up, I'm sure we have it in the notes, there's a trig identity where essentially you have a cosine of A times the cosine of B, and it comes up into sum and difference rules and leads to, again, terms which are sinusoidal, pure sinusoids, not the square, but sinusoids, with harmonics that correspond to sum and differences, which again will correspond to an inner number of cycles within one cycle for each within the period. Okay, and again, because when you integrate an even number of, or not even, just an integer number of cycles, or not a fraction, but an exact cycles, number of them, you always get 0 for the picture for the reason the picture is shown here. Now I realize I'm not doing this in the extreme detail, but I'm trusting you get the idea. And if not, speak up. Not hearing any question on that. So we would have, as long as the n is not equal to m, we will also have this orthogonality. And if we can say it's true for the cosines, pairing up cosines, then we should be able to say it's true for pairing up sines. Any questions? Now, I think these are the set of rules that we would need to generate, in fact, everything we need, that I believe we need is there, to generate the recipe for, let's say, the coefficient a sub n. So let's say, for example, my goal would be to use this idea to come up with a formula for predicting a sub n. And of course, that's what I plan to do with your help. Any questions? So let's, since this is the beginning here, the first application of these ideas is with the basic Fourier series, which I show here. And again, I'm thinking, here's our goal is to get a recipe for that a sub n, that we confidently, if we know the x of t, we can plug the x of t in and we can compute the a sub n. So I will do the following, and it's imagine this is an expression on the left, expression on the right, and I'm going to apply the inner product with the cosine n omega naught n prime. I mean, that's important. Not the same as dn. This is maybe a potentially. See here, just for emphasis, we know the n is tied to the index. Okay, so that as that n will be changing in that sum. Now I'm picking a particular n prime to do this with. Okay, which is not the same as the n here. So if you didn't do it this way, it doesn't work right. So in order to make the argument work right, you've got to take an n prime, which presumably could be any one of these n's, but you don't want to use the symbol n because it gets confusing and doesn't work. So we're going to make it n prime. For example, maybe n prime is 5, even though this n is allowed to go from 1 to infinity. Speak up if that's not clear. There's a difference between the n in that expression and the n prime here. So in general, they're not the same. Although presumably for one case in that sum, they would be the same. All right. So I'm doing the inner product coming in from the right into that expression, as you can see. And I'm thinking of the constant in front, A0, could be thought of, as we know, 1 times anything is anything. So we can imagine that the 1 vector up here at the top is in fact our basis vector that is involved with the A0. Okay. And then the fact is that the inner product is a linear operation. You know, in other words, let's put it this way, and I think you convince yourself it's right. Now write it up here at the top, and you know what I mean. F dot G plus H is equal to, and I bet you can guess this, most of you, F dot G plus F dot inner product H. Okay. So basically the dot product, if you can distribute it to 2, you can distribute it to all the terms. It's really a linear operation because based on integration. So it may not be a surprise because of that linearity in the definition of the inner product that when you apply the cosine of inner product with the cosine from the right, then when that first term we talked about, the second term involves this one right here. You could argue because it's linear, that coefficient a sub n can come out. And so the only thing left is term by term, you get the inner product between the cosine of n omega naught t and the cosine of n omega naught t. Now notice again, here it's important. You keep the n and the n prime distinct. They're not the same n in general. And the third term is down here at the bottom. Do the same thing. But this case, it's the sine with the cosine. Any questions? Okay, so if we look at this, what greatly simplifies what we have to realize is really right up here at the top. If everybody see that right there, okay. If there's part of the page you can't see, let me know that you think you're missing. Okay, so we're going to need this up at the top when we simplify this. All right. Okay, I'm waiting. Any questions?
No.
So anyone out there, what should happen to the first term? Any guesses? Anybody still there?
Zero's out.
It zeroes out, that's correct. And that's because of that property, the first line at the top, because of the one dot, or one inner product. Okay, so, but before I go on, any questions about that answer, which is correct?
So the n and the n prime would be the same right there?
The n and the n prime are not the same in general.
Okay.
Now, I want to say in general. Now,
Yeah.
I'm not saying that there won't be one value of n that will just happen to be the same as n prime. So you have to think of the n prime as fixed and the n is sort of like a variable. It could be 5 or 6 or 7 or 8, but maybe the n prime is just simply fixed at 5. Did that help a little? I don't know. See, the n prime would be fixed in this,
Okay.
I mean, at this point.
Right. Okay.
And then we'll see, we'll back up and kind of turn it into a general formula later. But at this point, you need to think of it as the one that's fixed, while the n itself, because it's the index at which goes with the summation, is actually changing. Okay, so.
I have another question. Sorry to interrupt you.
Okay, no.
Those properties you've written in the middle of the page, 1 dot cos n omega t, yes, those 5. Now the first 2, they're pretty obvious.
Okay.
But the next three, you said we'll cover them later. Do you have
No, I
like,
didn't mean cover later. Actually, I was thinking we had covered it. It's based on, and I think it's in my notes here if I can find them real quick. And I thought we had.
is there like an expansion of them you have given down somewhere in the notes that I haven't?
I'm sure it's in the notes somewhere. Oh, wait. Here's for example. Let me see. Yeah. Okay. Here's a. I mean, there's the one for the. Actually, three of them at least are here. Three of the ones I had in mind are here. Here you have the trig rule for the sine A, cosine B. Here you have the trig rule for cosine A, cosine B. Here you have the trig rule for sine A, sine B. And these are the ones I'm thinking of. Those are the formulas are the which when you use that, then it's that's it, I think. Does that answer your question or not?
Yes, it does.
Okay. Okay, so correctly, we figured out the first term is 0. Let's go to the third term because what should the third term be? And here, 1, 2, 3, the one on the bottom. Everybody see it? This one right here. What should that?
Zeroes out as well.
0.
Correct. Why?
Because of the identity.
Yeah, line 3. Line 3 is the right one. This 1, 2, 3. That's right. The third one at the top tells you that has to be 0. And that means if it's 0 for every n and n prime, then you don't have to worry, it's gone away. That term's gone away. So all we have is the middle sum, right? The middle sum. This is what I'm trying to speak up if that's not clear. So we saw that this one went to 0. We saw this one went to 0. And then all we have left now is that middle term.
Okay, quick question regarding the middle term.
Okay.
So you have cos n omega naught t product cos n prime omega naught t. Now,
Correct.
n is not equivalent to n prime.
Where n is not, well, let's put it this way. We're not saying it's not equal to n prime in general. What we're saying is that n can vary over all the integers from 1 to infinity, but we're thinking of n prime as being a select integer somewhere in there. It could be 5, could be 10, doesn't matter. But it's not in general the same as n prime because n prime is changing with a sum. It's the index on the sum.
Okay, so when
n is changing with the index on the sum and n prime is fixed. That's what I'm trying to say.
okay, so when we evaluate this whole thing, are we basically, the reason I'm asking this is the fourth line, the fourth identity, it states that it is 0 when n is not equal to m. So do we evaluate this when n is equal to n prime then?
Yeah, later on, it turns out you'll see that coming. When n is equal to m, we will need to evaluate it, but that we don't need that yet, but it is coming.
Okay,
It is coming.
thank you.
So, but what we do need to do is recognize one fact. If n is not equal to n prime, for the most part, almost essentially all the terms there except for 1, n and n prime will be different. For all those terms, you could say that particular inner product should be
0.
0. And which line are you thinking about? Number up here at the
4.
top?
4.
4, correct. That's where n is not equal to m. So that is really, that's exactly right. So, however, we cannot make that statement if n is equal to n prime. Because at this point you say, well, there's no information about that, and I would not argue with you on the fact that we know that we cannot make that claim when n is equal to n prime. But that's okay, in a sense, right now. What we've done is we've gotten rid of all those terms where n is not equal to n prime. Okay, so we're only going to have left is one term in that sum, right? And that's the term where n is equal to
N prime.
n prime.
Yeah, that is a question I was asking or getting at.
And then we will have to evaluate it. But that'll come. That'll come. Okay, any questions so far? So we've done a lot in terms of knocking out all the possible terms that could cause that we really don't need or don't want. And really the only term left, I contend, the only term left will be from this sum when n is equal to n prime. Now, if n is equal to n prime, then it's no longer correct to keep the a sub n and let the subscript n remain n. We now have to say that particular term when n is equal to n prime will be that term which has its coefficient a sub n equal to a sub n prime. And then which we see is here. So out of all those terms, this one survives. And yes, from the one at the top, we get a 0, and the one at the bottom, we got a 0. And on the left, we have that inner product rule that we started with. Any questions? I'm not hearing any questions. I'm not sure how good or bad that is, but anyway, I'm going to go ahead because we're almost to the point we got our answer. Okay, so as you might guess, hopefully, in order to, how much more time have I got left? I got another 5 minutes, I think. Is that correct? 5 minutes?
Yes.
Okay.
5 minutes, yes.
I think we can finish this in 5. Okay, so as you might guess, in order to make progress on this, to solve for the an prime, what we need to do is to evaluate what this is, right? I mean, that's kind of like was the heart of the previous question, and that is indeed at the heart of what faces us to do now. So you could argue, well, what is that? Well, we can use our definition for inner product, and we would say, well, that means you've got to take the product of the two functions and integrate over T naught, let's say the period. So if we use our, since it's cosine squared, and I guess all of you becoming experts at expansion of the cosine square, you know that the cosine squared of x is 1 plus the cosine 2x divided by 2. So you can write that as 1 plus the cosine 2, there's a 2 n prime omega naught t, and then divided by 2. Okay. Now clearly, or not so clearly, it's the integral of two terms. You can break up 1/2 and then the cosine of 2 n prime omega naught t over 2, and then you got two integrals, one of which is guaranteed to be 0. Which one is it, the first or the second? First being the 1/2, and the second being one with the sinusoid.
The second.
The second is the one, right? Right time to speak up if that's not clear. Second is the right one. And that's because the same argument, if it's, you're going to get an integer number of cycles being integrated over a time interval of the period, and ergo, okay, that means the same amount of area, positive is negative, and therefore it's going to be 0. And that's correct. So all that is left is the first term. And now if you look at the first term, you've got a 1/2 there, right? So, and you just, doesn't require a table of integrals. 1/2 integral dt, so you basically, and that symbol there represents any time interval of length t naught. So the integral dt is just going to give you t naught, whether you started from 0 to t naught or minus t naught over 2 to t naught over 2. Doesn't matter, that integral is going to give you essentially a t naught, and there's your factor of 2. So you get t naught divided by 2. Any question on that?
No.
Actually, yeah, what happens on the left side
The left side, which left side?
of the equation? The cosine n prime.
Okay, this one here?
Yeah.
Here? Okay, so what's the question?
Does that, is it equal to like that?
Yeah, so what am I using here? Well, I'm using this you say, well, where did that come from? And that's a good point. It actually came from our definition of inner product. I recognize, first off, that both functions are strictly, I guess you can't read my mind. strictly real. Therefore, there's no complex conjugate required. You can do complex conjugate, won't make any difference. We can see that both functions are the same. And so really what happened was you just ended up doing the cosine squared. And there's your argument for both these should be the same, n prime omega naught t, n prime omega naught t.
Okay.
Does that help at all?
Yeah.
Okay, all right. And then from there, you're okay?
Yes.
Okay, okay. Let's see, so then the few and last steps to get to the formula that we want, if we go back for a moment and say, okay, we actually have we go back to this line right here. We worked hard to figure out, and I'm going to write it on top of here. We worked hard to figure out that this operation right here gives us a factor of T naught divided by 2. Okay, and that was right there. Okay, we did that. So now we're set to rock and roll and solve for the AN prime, because all we have to do is then divide both sides by T naught divided by 2. Any question about that? Now, the only thing is you might notice, not to slip one past you, notice I wrote it as x inner product cosine of n prime omega naught t, and really no big change. I wrote it vice versa because I know that as long as the functions are real, the inner product is commutative. Doesn't matter which order I put them in. Any questions? We're not quite there, but we're almost there. So if we pull up our handy dandy Swiss knife of formulas for inner product, we see, in fact, going back to this one, we can use for the f, we can use our cosine n prime omega naught t, and for our g, we can use x of t and just plug it in. And we see that we have a factor of, and that's that part right there. We have a factor of T naught over 2. We can bring the 2 to the numerator and come up with this formula right here. Now you could say, well, that's perfectly reasonable. And it would be not incorrect. However, most people would say, well, you know, if you look in tables, they don't have an AN prime, they've got an AN. And being older and wiser, we all know that, well, that's just a symbol. So we don't really need to be attached to that prime too much, so we can drop it. And we'll let the n prime go to n, and we get our formula for the A coefficients for the basic trig would look like this. And not to bore you too much with the details, but I'm thinking if you understand those steps, you might appreciate the fact you can repeat them. Not in terms of using a cosine with the inner product, but using a sine and do all the same steps. You can get a formula for the B coefficients, which looks almost the same, except for instead of a cosine, you got a sine. How much time I got left?
We passed like 5 minutes.
Minus 1 minute or 5 more minutes? Or
minus 7 minutes.
Minus 7? Oh, I'm surprised you didn't shoot me. Okay, well, sorry about that. If you have any last, class then is over. I want to remind you, if you can bring back your questions from, is it homework 4? I think homework 4. Then I can answer those, and we can move along on the game plan. That'll be on Wednesday. And here for a few more minutes. You got questions on the material?
Do we have anything due next week for signals? Just a recap.
Well, I mean, the good news is you've already turned in your MATLAB, so that's not, you don't have that due. No, really, the only thing on our agenda is to keep moving on our homework, so we're ready for another midterm.
Wait, what MATLAB?
Oh no, I'm saying I'm threw that out. I said you already finished your MATLAB.
Yeah, we had a signals one due like a long time ago. Remember?
Yeah, that was
long time ago.
Oh, the one that was out of 55 points?
What?
The one that was 55 points?
5 points? What 5 points?
No,
Oh,
55.
55.
Oh, 55, that's correct. That one's already done. So really, the only thing that's going to become due is we're going to just go through the same kind of thing with the quizzes, I guess, that we did in the 4308 class, which is go over the homeworks, give you a chance to ask questions. And then I put a quiz on Canvas, for example, which you're allowed to turn in using the upload process that hopefully by that time you're familiar with. And then at some point we get typically 3 homeworks finished, then we can have another midterm. I
Okay,
won't
sounds
swear on that number, but I think that 3 is often used. Sometimes it's only 2, sometimes it's 2, but could be 3. Anyway, the point that's how I see it happening. Did I answer your question about anything due?
Yes.
Okay.
Yes.
So I'd say anything due is, well, yes, you have something due. You should try the homework 4 on your own first before you look at them. So you can see, well, where am I confused on doing this if I just read it without any help from the solutions? And then after you make a good stab at it, take a look at the solutions. If you still feel stuck, or even if you want to check what you wrote down. I think that's always a good plan. And so for references, I'm going to plan on starting with the, how do you, see, one thing we did not do, we didn't find the A0. Won't take long to get that one. But since we're over class time, we'll pick that up on Wednesday.
So the AN and BN was that we found were only for the basic or the trig.
Yeah, that's right. It's a bootstrap process. Once we get those, then we can move right along to get the compact Fourier series coefficients. And that's why we do it the order we do it.
Okay.
Any other questions? Okay, well, I'll be back here on Wednesday for sure. And I do have I'm looking at the possibilities for quote unquote kind of an office hour type situation with Zoom. Haven't figured it out, but I'm thinking about it. I think I'll have a plan in the early part of this week, probably by Wednesday, almost certainly. Okay, any other questions? All right, and I'll see you Wednesday. I guess meeting over is supposed to be. Let's see here.